big unit of the year, congrats, we've made it through another packet of Cornell notes, is waves. And you'll see there's a lot of overlap with the waves unit to our energy unit, to our electricity and magnetism unit, and a little bit with mechanics as well. But for now, we're just going to go through the first couple of pages of our Cornell notes, and we will expand on this on Thursday. So a wave is a vibratory disturbance that propagates through a medium. Propagates is a word that comes up a lot when we're talking about waves, but for now you can just think of it as moves through. So a vibratory disturbance that moves through a medium. And what is a medium is hopefully what you're asking, but a medium is just a body of matter. So I'm going to come back to that, but like outer space is a vacuum where there's no matter. And so outer space, there's no medium. But waves and energy transfer. Waves transfer energy from one place to another by repeated small vibrations of particles of a medium. A source may provide the initial disturbance, but no mass is transferred. And that's really important. There'll be questions that come up where energy is transferred, but mass isn't. Now, two main types of waves are mechanical waves, which are sound waves, which is what you're hearing right now. Water waves is another example. They require a medium to move or to propagate. And then electromagnetic waves, an example of this would be light waves, radio waves, ultraviolet, anything on the electromagnetic spectrum. They can travel through a vacuum. So we obviously can get light from the sun, so electromagnetic waves can travel through outer space, but for example, sound waves would not be able to. Okay, next little segment, pulses and periodic waves. And a pulse is a single short disturbance that moves from one position to another in a field or medium. So we might see a wave like this, but a pulse is just one short disturbance that moves, through a medium. Now, reflection is just a rebounding of a pulse or wave as it strikes a barrier. And I'm not going to tell you the rules for when or how it works when waves are reflected. You're going to do a little activity on Thursday to make this conclusion on your own. But let's say we have picture A over here. This will be the before, and we have a pulse moving towards this barrier. This would be called the incident pulse. And then if it's reflected, sometimes, not always, again, you're going to figure this out, the reflected pulse will be inverted like this. And then a periodic wave is just a series of regularly repeated disturbances of a field or medium. So if something's happening over and over again at regular intervals, that can be classified as a periodic wave. And move on to our types of waves. And for now, there's going to be two types of wave motion that we're going to focus on. The first one is longitudinal waves, where this is a wave in which the motion of the vibratory disturbance is parallel to the direction of motion. And a transverse wave is the motion of a vibratory disturbance is perpendicular at right angles to the direction of travel of the wave. Easy way to remember this, if we take the first letter in the word transverse, so we take this T and we write it upside down, Well, boom, there is our symbol for perpendicular. So transverse, look at that T, and you'll remember that it is perpendicular. Now, what exactly does this mean? So I'm going to draw pictures in each of these boxes to help us kind of visualize. But a longitudinal wave, we'll say the wave motion is to the right. And here we'll have a bunch of lines. They're going to start spreading out. Now, the direction of the wave motion, let's say we have, I don't know, a point A in space. In a longitudinal wave that's moving to the right, point A is free to move left and right in a parallel direction to that wave motion. Just expanding a little bit, where these lines are spread apart, that's going to be called rarefaction. And then where they're really close together, here and here, this is going to be called a condensation. That says condensation. You just have to take my word for it. Now, on to our next example of a transverse wave. And again, this is perpendicular. And we see transverse waves like this. And again, this wave is still moving to the right. So we'll, wave motion to the right. And then if we have point A at this spot on the wave, this is free to move up and down. Point A cannot move left or right, but it can move up and down. And I don't know, one way you can kind of picture this, if you've ever been a water park and a wave pool, when that wave passes by you, you go straight up and down. Okay, so our last portion of waves that we're going to focus on for our first section of the Cornell Notes is characteristics of periodic waves, which can be a lot of fun to study with slinkies and whatnot. So frequency is just going to be the number of cycles or complete vibrations per unit time. And frequency, number of cycles per unit time, the units are going to be 1 over s per unit time, or this is also known as, so 1 over second is equal to Hc, which is hertz. In a period, we may have seen this a little bit when we were studying pendulums at the end of the energy unit, but period is just the time for one complete vibration or cycle. That's a word we'll commonly see or frequently see throughout this unit. And the formula for a period, if you remember to the pendulum, T equals 2 pi square root of L over G. That's a capital T. For waves, the period is just going to be equal to 1 over the frequency. And the units for period are seconds. Now, the amplitude of a mechanical wave is the maximum displacement of a particle of the medium from its rest position or equilibrium position. Now, amplitude is related to the amount of energy that a wave transmits. If we're talking about light waves, we're talking about the brightness intensity. So a higher amplitude for a light wave would correspond to a brighter light. But for a sound wave, think electric guitars. You plug them into an amp. So for sound waves, the higher the amplitude, the louder that the sound is going to be. And if we go back, we may see an example like this. If this is a transverse wave, we may see it graphed like this. and maybe this is 0.5 meters, and this is negative 0.5 meters. We'll have time on the x-axis. The amplitude is the maximum displacement from the rest position, and the rest position is along the x-axis. So for this example, the amplitude would be 0.5 meters for this transverse wave. Now, when we're talking about longitudinal waves, the amplitude is going to be the distance between the rarefactions and the condensations, as you can see by the red line. So therefore, a higher amplitude for a sound wave means that the condensations and rarefactions are spread out more. Phase means that points on successive wave cycles that are displaced from their rest position by the same amount. In other words, one wavelength apart. And I'm going to draw a picture in a second to help us visualize that. And it's good to introduce in phase before wavelength, because wavelength is the distance between any two successive points in phase. So when we're talking about transverse waves, if I have, let's just say I have a nice transverse wave. Now these points are called a crest, and the points below the x-axis are called a trough. I always think about farm animals, they drink out of a trough. So if we fill this up with water, we would see that that is below the x-axis. So it kind of looks like one of those. But a wavelength is the same position. So any two crests are one wavelength apart. And same with a trough. So any of these points are one wavelength apart. We could also say, okay, well, at this point, it's beginning to move upwards. Here, we're moving downwards, so that doesn't work. But as soon as we get here, that's also moving upwards. So this would also be equal to one wavelength. So one wave contains one crest and one trough. So that is what one wavelength looks like. Now, any two points that are exactly one wavelength apart are said to be in phase. So if we had point A here and point B here, A and B are in phase. But if I placed, let's say, point C, B and C are not in phase, since they are not one complete wavelength apart. Now, if we have say two transverse waves here, it's like going in a complete circle. So this would be one wavelength from there to there. Let me use a different color. So the red to red would be one wavelength. Now, 0 degrees, halfway would be 180 degrees, and then a complete cycle would be 360 degrees. Now, if we had, say, point A here and point B here, point A and B would be called 180 degrees out of phase, because they are not complete wavelength apart. And hopefully that makes a little sense. We will do plenty of examples where this will get cleared up. And then let's just mention a longitudinal wave, where here, obviously, that we don't have rarefactions. We only have one in this diagram, but one complete wavelength in here would be the distance between two condensations. So for a longitudinal wave, this red line to red line would be one wavelength. And wavelength is measured in meters. So always in meters. Okay, and the last thing that we're going to introduce, we'll do the sample problem together on Thursday. But for the speed of waves, again, speed, it's a scalar, but it's going to be measured in meters per second. And in your reference table, you can find this formula, but the speed or velocity of a wave is equal to f, the frequency, times lambda, which is the wavelength in meters.